Properties of non-singular matrices and determinants. Welcome, everyone. Let's begin our session on the properties of non-singular matrices and determinants. Before we dive into our new material, let's quickly recap what we've already learned. In our previous lesson, we established a very important definition. A square matrix, which we'll call A, is classified as non-singular specifically when its determinant is not equal to 0. In mathematical terms, we write this as the determinant of A does not equal 0. Now, why does this specific condition matter so much? Well, it is absolutely crucial because this is the primary requirement that allows a matrix to have an inverse. Without a non-zero determinant, we simply cannot perform certain essential operations. So, moving forward into this new subsection, our goal is to see how this property of non-singularity behaves when we start multiplying two matrices together. We are also going to explore a fundamental and very powerful property regarding the determinant of a product of matrices. Let's get started. The determinant of a product of matrices. Now that we've established what it means for a matrix to be non-singular, specifically that its determinant isn't 0, let's move on to one of the most powerful properties in matrix algebra. This property describes the beautiful relationship between the determinant of a product of two matrices and the product of their individual determinants. Here is the property itself. If we have two square matrices, let's call them A and B, and they are of the same order, then the determinant of their product, which we write as a times B, is exactly equal to the product of their individual determinants. In mathematical notation, we express this as the determinant of a times B equals the determinant of A multiplied by the determinant of B. To make sure this is clear, let's break it down into two different approaches you can take. First, you could perform the matrix multiplication of matrix A and matrix B to produce a brand new matrix, which we can call matrix C. Once you have that new matrix, you can then calculate its determinant. Alternatively, you can take a much simpler route. You can calculate the determinant of matrix A and the determinant of matrix B separately. Since these determinants are just individual scalar numbers, you can simply multiply those two numbers together. The most important thing to remember is that both of these methods will yield the exact same result. This shortcut is going to be incredibly useful in the next few slides when we look at how non-singularity is preserved during multiplication. Product of two non-singular matrices. Now that we have established the rule for the determinant of a product in the previous slide, let's use that rule to derive a very important conclusion about the nature of non-singular matrices. Here, we have a formal theorem to discuss. The theorem states that if matrix A and matrix B are both non-singular matrices of the same order, then their product, a times B, is also guaranteed to be a non-singular matrix. To understand why this is true, let's walk through a step-by-step logical proof. First, let's look at what we are given. We are given that matrix A is non-singular, which, as we learned in our first slide, means that the determinant of A is not equal to 0. Similarly, we are given that matrix B is non-singular, which means the determinant of B is also not equal to 0. Next, let's consider the product of these two scalars. Since neither the determinant of A nor the determinant of B is 0, it follows mathematically that their product, the determinant of A multiplied by the determinant of B, must also be non-zero. In other words, a determinant times B determinant does not equal 0. Now, we apply the property we just discussed in the previous slide. We know that the determinant of the product, A times B, is exactly equal to the product of the individual determinants, a determinant times B determinant. Finally, we reach our conclusion. Because we have already established that this product of determinants is not 0, it follows that the determinant of the product matrix, A times B, cannot be 0 either. Therefore, by the very definition we started with, the matrix A times B must be non-singular. To help this concept stick, in the next slide, I'll provide a real-world analogy that makes this logic even more intuitive. Real-world analogy. Think of a non-singular matrix simply as a reversible process. In mathematics, when we say a matrix is non-singular, we are essentially saying that the transformation it performs can be undone. To connect this to what we just discussed regarding the product of matrices, imagine you have two separate processes. Let's call them matrix A and matrix B if both of these individual processes are completely reversible, meaning they are both non-singular. Then performing them one after the other, which is what the product OB represents, results in a combined process that is also completely reversible. Now, before we dive into the heavy calculations in the next few slides, let's take a moment to step away from the numbers and look at the bigger picture with a real-world analogy. In short, if you start with two reversible steps, your final result will never lose that ability to be undone. This intuition will help you understand why the product of two non-singular matrices must, by definition, also be non-singular, a concept we are about to prove formally in the next slide. Illustrative example. Now that we have understood the theory and the logical proof behind why the product of non-singular matrices remains non-singular, let's put this into practice. To truly see this property in action, let us verify the property that the determinant of a times b equals the determinant of a times the determinant of b with a concrete numerical example. For this demonstration, I am providing us with two given matrices. Matrix A is a 2x2 matrix with the first row being 1, 2, and the second row being 3, 4. Matrix B is also a 2x2 matrix, where the first row consists of 2, 1, and the second row consists of 0, 5. In the next few slides, we will calculate the determinants individually, and then compare them to the determinant of their product to see if they match. Step-by-step calculation of determinants. First, we'll start with step 1, where we calculate the determinant of matrix A looking at our values. We take 1 times 4, then subtract 2 times 3. This gives us 4 minus 6, which results in a determinant of -2. Next, in step 2, we perform the same process for matrix B. We multiply 2 by 5 and subtract 1 times 0. This leaves us with 10 minus 0, so the determinant of matrix B is 10. Now that we have our two matrices, A and B, let's move into the actual calculations to see this property in action. Keep these two results in mind, because in the next step, we are going to multiply them together before we even touch the product matrix itself. Product of determinants and matrix multiplication. Now that we have calculated the individual determinants for matrix A and matrix B on the previous slide, let's move on to step 3. We are going to find the product of these two determinants. Since we found that the determinant of A is -2 and the determinant of B is 10, we simply multiply them together. -2 times 10 gives us a result of -20. Next, let's proceed to step 4, where we will find the actual product matrix, OB. To do this, we perform matrix multiplication using our original matrices. We take matrix A, which has 1, 2, 3, and 4, and multiply it by matrix B, which has 2, 1, 0, and 5. To find the elements of our new matrix, we multiply the rows of the first matrix by the columns of the second. For the top left element, we take 1 times 2 plus 2 times 0. For the top right element, we calculate 1 times 1 plus 2 times 5. Moving to the bottom row, the bottom left element is 3 times 2 plus 4 times 0, and the bottom right element is 3 times 1 plus 4 times 5. After performing these arithmetic operations, we arrive at our resulting product matrix OB, which consists of the elements 2, 11, 6, and 23. Now, in the next slide, we will take this new matrix and calculate its determinant to see if it matches the product we found in step 3. Determinant of the product matrix. Now, we have reached the final step of our numerical verification. In step 5, we need to calculate the determinant of the product matrix we just found, which is the determinant of a times b. Looking at our matrix OB, we multiply the top left element, 2, by the bottom right element, 23, and then subtract the product of the top right element, 11, and the bottom left element, 6. This gives us 46 minus 66, which results in -20. Now, let's look at our final observation. If we compare this result to what we calculated earlier in step 3, we can see that the determinant of ob is -20, and the product of the individual determinants, a and b, was also -20. This perfectly verifies our property. The determinant of the product equals the product of the determinants. Furthermore, notice that because this determinant is not equal to 0, we can conclude that the product matrix itself is non-singular. This leads us directly into our summary of key takeaways. Key takeaways. First, remember the determinant product rule. This is the core concept we've been discussing. The determinant of the product of two square matrices is exactly equal to the product of their individual determinants. In mathematical terms, the determinant of a times b equals the determinant of a, multiplied by the determinant of b. Second, we have the principle of the preservation of non-singularity. As we proved in our logical breakdown earlier, if you start with two matrices, A and B, that are both non-singular, you are guaranteed that their product, ob, will also be non-singular. The property of being invertible is preserved through multiplication. Finally, I want to emphasize the scalar nature of these values to avoid any notation confusion. It is vital to remember that the determinant of A and the determinant of B are scalar values, meaning they are just single numbers. On the other hand, the product ob is a matrix. Keeping this distinction clear will help you avoid the common mistakes we are about to discuss in the next slide. All right, we have worked through the calculations and seen the property in action, so let's wrap everything up by reviewing our key takeaways. Common mistakes. First, watch out for confusing addition with multiplication. It is a very common error to assume that the determinant of a sum is equal to the sum of the individual determinants. I want to emphasize this clearly. The determinant of a plus b is not equal to the determinant of a plus the determinant of b in general. This beautiful property we explored today, where we can split the determinant, applies strictly to multiplication, not addition. Second, be mindful of your order of operations dollar and efficiency. Sometimes, students try to find the inverse of matrix A and the inverse of matrix B first, and then attempt to find the determinant of the product. While mathematically possible, it is unnecessarily complex and time-consuming. As we saw in our numerical example, it is much simpler and more direct to always use the property that the determinant of a times b equals the determinant of a times the determinant of b. Finally, be careful with your notation to avoid confusion. Do not confuse the notation of the determinant of a times b, which is written as the vertical bars around a times b, with the product of the matrices themselves, which is just a times b. Remember, the determinant of a times b results in a single scalar number, whereas the product a times b results in a new matrix. Keeping this distinction clear is vital for your accuracy in exams. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. Even the most diligent students can stumble on these three specific areas, so please pay close attention. That concludes our session on the properties of non-singular matrices. Great job today!